Here I have a classic problem involving the force of friction and how it acts on everyday situations. Here's a car traveling the road in principle with some initial velocity. And the friction force is going to act on the car in such a way to slow the car down. So the first thing I want to do, obviously, is to draw a free body diagram to consider all of the forces that affect the motion of the car. Naturally, the car has weight, so I have a weight vector, mg, directed downward. The car is sitting on the ground, so I have a normal force directed upward, perpendicular to the ground. And I have the friction force, which I draw directed to the left when the car is traveling to the right, because I presume that it's this friction force that is going to cause the car to slow. There has to be some force that causes the car to stop. A couple things that you don't see on this free body diagram, for example, is the force of tension. There are no ropes attached to the thing. Also, there's no viscous drag force because I'm not considering viscous drag in the problem. More importantly, there is no push force forward on the car. Typically, in order to make a car accelerate forward, I need a force in the direction of motion to create that acceleration. That would be the force of friction, but that's not what's happening in this particular case. In this case, the car is skidding to a stop. To understand the physics of this, I'm going to write Newton's second law. I could write Newton's second law for the vertical direction, right? Because I want to apply Newton's second law to my two coordinate directions. I have two coordinate directions here, the vertical direction and the horizontal direction. But look at the free body diagram. It clearly shows that the normal force directed upward must be equal to the weight force directed downward. I don't necessarily have to write that as an equation, but it's pretty clear that in order to support the weight of the car, the road has to push upward on the car with a force that's equal to the weight of the car. And so just by looking at my free body diagram, I can tell that the normal force is equal to the weight. What I'm really interested in is the horizontal motion, and in particular, the horizontal acceleration. So I'll write Newton's second law for the horizontal direction. The sum of all forces is equal to the mass times the acceleration. Now, when I'm looking at only horizontal forces, there's only one, the force of friction. So the sum of the forces in this case is simply the negative friction force. I call it negative because it points to the left in the direction that I presume to be negative, because I would just take the direction of the car to be positive. Very sensible. That net force, which is just the friction force, is equal to the mass times the acceleration. So I write negative F is equal to mass times acceleration. Now the friction force, I learned, is equal to the coefficient of friction multiplied by the normal force. There's two kinds of coefficient of friction, kinetic and static. Since this car is skidding, the friction coefficient that I'm referring to here is the coefficient of kinetic friction. At any rate, I take one algebraic step by asserting that the friction force is equal to mu times the normal force, but I just got done making an argument that the normal force was equal to the weight. So replacing the normal force with m times g, I can now write that negative, the coefficient of friction, m times g is equal to m times a. I might have been a little concerned when I first read the problem because I wasn't given the mass. It's very common when I teach physics live that students say, yeah, I wanted to solve the problem, but I didn't know the mass. Sometimes I need to have the patience to follow the problem through until I realize, just as happens here, the mass appears on both sides of the equation and therefore cancels. So I have the mass on the left-hand side canceling the mass on the right-hand side. And what I've discovered is exactly what Isaac Newton promised me by formulating Newton's laws in the first place. By looking at the natural constraints or conditions that act on this object, I'm able to determine the acceleration, which is negative mu times g. I like the fact that it's negative, because in order for this car to slow down, I'm going to have to subtract velocity in every moment. I have enough information in the problem to calculate how much acceleration there is, and once I know it, once I know that acceleration, then the problem becomes kinematic, and you'll find that a lot of answers can be determined simply by now asserting v squared is equal to v naught squared plus 2a delta x, a kinematic equation that we're familiar with using. In this case, we're going to skid to a stop, so set the final velocity equal to 0 and calculate the length of the skid. By the way, I think the very next problem in the assignment is this same problem, but the car is accelerating instead of skidding to a stop. In order to accelerate, a car requires friction force forward. the way that this happens is according to Newton's third law. The car pushes backward on the earth with static friction force, and the earth pushes forward on the car with static friction force. You might be surprised to hear me say static friction in that case, because after all, the car is moving. Well, sure, the car is rolling along, but if you look closely at the tires on the road, because the situation is a situation of not skidding, there's no relative motion between the tires and the asphalt, and therefore the nature of the friction force is static. The nature of the friction force is non-slipping. A challenge that suddenly appears in this homework assignment is this bit of weirdness. There's a 30-kilogram block that's sitting on a surface that is frictional. And there's a rope attached to it, and that rope has 125 newtons of force. I'm going to refer to that 125 newtons of force as a tension force. So you'll see me refer to it as capital T. So as I pull the thing along with 125 newtons to the right, there's friction force directed to the left, and the thing may remain stationary if the static frictional force is enough to prevent it from moving, or it may move along at constant speed if the kinetic friction force is exactly equal to the tension force, or if the tension force is greater than that kinetic friction force, it may accelerate along. I don't know what's happening here unless I'm told by the problem statement what to expect. And then I have this extra wrinkle here where I have a force pushing down on it. Imagine that this situation happened in real life, and there's a thing, object that's sitting on a table, and there's a rope attached to it, and your friend is trying to pull it away, and you want to stop them. Well, the very first thing that you would do is put your hand on top of it and push downward, because you have an instinct that tells you what our free body diagram is about to tell us, that pushing downward with a force F will ultimately increase the normal force, which will increase the friction force, which will prevent the thing from moving. And in fact, in the problem, that's what happens. We want to know how hard do you have to press downward to prevent the thing from sliding. In order to answer the question, I'm going to need to have a good free body diagram so that I can apply Newton's second law, so that I can see what those equations tell me about the behavior of the system. So here's my free body diagram. I have the normal force directed upward and the weight force directed downward. But now I've added that extra push force from above directed downward. You'll notice that I didn't do like the picture did and draw the arrow pointing at the block. You can do that if you want to. Experience has shown me it's kind of a bad idea. I like to always keep my force vectors pointing away from the object. I find that that's, visually a bit more clear. And gets me better organized. So I have that push force from above downward. Now, what that means is that the normal force pointing upward is affected by that push force F downward. Earlier in this video, I did a problem with a car sitting on the road, and the normal force upward was equal to the weight downward, because they were the only two forces acting vertically. But now, there's a little extra push force downward. Horizontally, I have the tension force, which is given, I think, 125 newtons. That tension force pulling to the right, and then I have a friction force directed to the left. So I'm going to write Newton's second law, but this time I'm going to write it for both coordinate directions. For the horizontal direction, I write all of the sum of the forces that act along the x-axis is equal to the mass times the acceleration along the x-axis. So here, the tension force, which points in the positive direction, minus the static friction force, as it happens, directed to the left, is equal to the mass times the acceleration along the x-axis. Now, I'm not in this video solving these problems for you. I'm pretty sure the acceleration is equal to 0 in both directions. So I think this max is in fact equal to 0, because I don't think in this problem the box moves at all. I'm going to check to make sure that I'm right about that. Along the y-axis, I know that it doesn't accelerate vertically. So when I write the sum of the forces along the y is equal to the mass times the acceleration along the y-axis. I'm going to write the normal force upward as a positive force, both F and mg downward as negative forces. And I set that equal to the mass times the vertical acceleration. But that vertical acceleration is in fact equal to 0. Using these two equations together, I should be able to work out how much friction force is required. And if I know how much friction force is required, then I can work out what the coefficient of friction must be, or as in the case here, I'm looking for the force capital F. So all I have to do is take these equations and rearrange them judiciously to uncover that force. Here I have a case of a crate that is being pushed by one person from behind and pulled using a rope by another person from the front. I imagine that it's moving to the right in this depiction that I've drawn here. The key thing is, and the thing you have to watch out for, is very often in physics problems, and it's no less true with Newton's second law problems, is that sometimes there's implied information that you have to look out for when you're doing your solving. Here, the implied information is, I'm told that they're pulling the thing along at constant speed. And I might read that and dismiss it, and then when I try to solve the problem, I find that it's difficult to do. The fact that it's moving at constant speed means the acceleration is equal to zero. Since the acceleration plays a big role in Newton's second law, that idea of the acceleration being zero is really important. As always, I start with a good free body diagram for this situation. I draw a box, and I draw all the forces that act on the box. Certainly the box has weight, mg, directed downward. It's sitting on the floor, and so there's a normal force directed upward. There are two forces directed to the right. One is the fellow on the left who's pushing it to the right, and the other is the fellow on the right who's pulling it to the right. Both of those influences act to the right. I call one of them a tension because it's a rope, and I call the other one just capital F because of push force. Both of these forces are opposed by a friction force that is directed to the left. Because the crate is sliding, I know that this friction force is kinetic frictional force. Also, looking at this free body diagram, this is another simple case where just by looking at the vertical forces on my free body diagram, I can tell that in this case, the normal force directed upward is equal to the weight force directed downward. So I need only apply Newton's second law to the horizontal direction. That's the direction that I'm interested in analyzing anyway. The sum of the forces that act horizontally, with to the right taken as the positive direction, is the positive tension force plus the positive push force minus the opposing friction force. That is the sum of the forces. That then is equal to m times a. But as I pointed out, in this problem, the acceleration is equal to zero. So m times a is zero. And now I can solve for whatever unknowns the question asks for. We finish up this assignment with a fairly challenging problem. It's challenging because the free body diagram is unfamiliar and I suppose a little bit difficult to draw for the introductory student. So our main focus is to make sure that we get the free body diagram of this problem right. Once I have the correct free body diagram, it's like every other Newton's second law problem. Newton's second law applied to the vertical direction, Newton's second law applied to the horizontal direction. And so we need a really, really good free body diagram to understand what's going on here. You'll see what I've done is drawn here a box that represents the box pushed up against the wall. The very first thing that I want to point out is that now the normal force is directed to the right. I've done a bunch of problems, and if I read about this physics, we see lots and lots of problems where the normal force is directed upward. This is usually because an object is setting on a horizontal surface that then pushes upward perpendicular to the horizontal surface. But this box is being pressed against a wall. And so the force of contact between the box and the wall is directed to the right, perpendicular to the wall. I also have the weight force directed downward because the fact that it's pressed against a wall does not change the fact that gravity is vertically downward. And so there my weight vector mg appears in the free body diagram. Now, I've got this push force that is pushing at an angle. And I remember back to when I did projectile motion problems, and I realized that to solve the problem when a projectile was launched with a velocity that was not horizontal, not vertical, but at an angle, the very first thing that I did was to find the components of that velocity and then solve the horizontal problem and solve the vertical problem independently. Well, I want to do the same thing here. I'm going to take that push force that's applied to this block and break it down into two components. A component that's directed toward the wall and a component that's directed upward, parallel to the wall. I can tell by looking at the orientation of the force in space and the location of the angle that it is the component of the force that is toward the wall that is the adjacent component, and therefore the cosine theta component, F cosine theta. The other component, therefore, the component that is upward and parallel to the wall, is the sine theta component. And I haven't calculated anything yet, but I noticed something almost immediately. Since this is a 1 kilogram block, it has a weight of about 10 newtons. If I take the 12 Newton applied force times the sine of 30 degrees, I find that that's 6 newtons of force. That means that this push force up the wall is not sufficient to hold the block in position. Make that realization. And yet I'm told that the block stays in position. There has to be an explanation for that. The explanation is that there is a static frictional force directed upward that, together with the F sine theta force, supports the weight of the object so that it doesn't fall. Applying Newton's second law to the vertical direction, F sine theta plus F minus mg, those are my vertical forces, F sine theta and F, both positive, directed upward, and mg negative because it's directed downward. That net force, that sum of forces, is equal to the mass times the acceleration. The acceleration is equal to 0 because I'm not moving anywhere. So that's a simplifying factor. You may wonder, I haven't used the horizontal at all. Well, look at the horizontal direction on this diagram, the toward the wall direction on the diagram. There are only two forces acting. The push force F cosine theta toward the wall and the normal force away. There's no acceleration horizontally. And so clearly, just by looking at my free body diagram, I can tell that the normal force is equal to F cosine theta. And it matters because inside of that friction force, lowercase f, I know that that friction is equal to the coefficient of friction multiplied by the normal force.